It's easy to create a confidence interval for a sample mean with the CImean function. There is one required argument, x. The x argument is set equal to the interval level variable to be analyzed. The CImean function has some standard optional arguments. With CImean, you have options to weight observations, specify the dataset name, the number of digits to display after the decimal point, and whether you want results printed to an HTML file in your working directory. The function also has some unique optional arguments. I will show you how to use the optional arguments named level and popsd in this video. The CImean function can also show the confidence interval of a sample mean on a plot. You can fine-tune that plot using the CImean's main, xlab, and xlim arguments. A couple of comments before we work through examples. First, notice that this function's name is capital C, capital I, M-E-A-N. Most companion functions have capital C on the end, but this one has capital C, capital I on the front. It just looked better that way and made more sense. Second, the CImean function is designed to analyze a dataset variable, find its mean, and report the confidence interval. If you're given a sample mean and its standard error and want to find its confidence interval, you can use the sampdisc function as a confidence interval calculator. So to see how to use the CImean function, let's work through some examples together. Okay, I'd like to show you how we can use the CImean function from the RCPA3 package to generate confidence intervals for sample means. Before the video started, I've installed the package and used the library command to load it. I'm going to run this help CImean command so we can look at the documentation for the function as we do the analysis. So to generate the confidence interval for a sample mean from observational level data in a data set, we would call the function by name CImean, and there's just one required argument, and we set x equal to the name of a variable in a data set that's measured at the interval level, which R would call a numeric, that we want. Why is it not popping up the menu there? That we want to obtain a confidence interval for. Okay, so that's what I was looking for. I was looking for the pop-up menu to auto complete this. So I want to look at I like this address years variable. It asks NES respondents how many years they've lived at their current address, and to make the results a little bit more useful to us, I'm going to add on the weights argument and set W equal to NES $weights, the weights variable in the NES dataset to weight the observations. Let's run it and look at the results. R returns a confidence interval of a mean, a table of the 95% confidence interval, and a plot. The plot looks pretty basic because there's only one number to return on the plot. So we've got the point estimate. That's what I want to start with, 11.987. So it says that the mean number of years NES respondents have lived at their current address is 11.98 years. And so that's the marker in the center of the plot. It's at 11.987. But given the variability of the sample and the number of respondents asked this question, it's plausible to think that the actual value in the population, number of years lived at their current address, the mean could be as low as 11.736 or could be as high as 12.238. So those are the values that are the lower bound of the confidence interval, the lowest number, that's on the dashed line, and as high as the upper bound, that's the top number, the dashed line. This is the marker, is the estimate we got from the sample, but it's plausible the actual value could be anywhere really along this line. That would be the 95% confidence level. So if we want to be 95% confident that the interval contains the true value in the population, we'd want to mark it between 11.736 on the lower end and then 12.238 on the upper end. Without knowing the true value in the population, that would be our interval for 95% confidence. It gives you an idea of how uncertain we are about the actual value. And a word of caution about these plots. So I think it's great to see the the confidence interval visually represented, the point in the dashed line, but the plot can be somewhat misleading because it's getting automatically rescaled every time you run it. So it rescales the x-axis, in this case, between 11.6 and some value out here, probably like 12.5, to fit whichever variable you're analyzing. And it will automatically do that and adjust based on the values. So all the confidence intervals of means are going to look pretty much the same way here, no bigger or wider, but whether it is a big number or a wide interval, you need to look at the scale, the actual scale that it's drawn on, to subjectively interpret the plot. Okay, we're looking at a confidence interval of the sample mean, the confidence interval for the sample mean number of years that NES respondents have lived at their current address. We have a table that shows a lower bound, point estimate, and upper bound. And then we see that represented on a plot here. The point estimate is the dot in the middle, and the dashed line segments mark the confidence interval. If we return to the documentation page for the CImean function, see some of our standard optional arguments. I've already used one, the W argument, for observation weights, and I've specified the weighting variable in the data set to get a weighted estimate. Also have a data argument and a digits argument. Those should be familiar to you already, as well as the print C argument. If you wanted to print the table as well as the plot to an HTML file in your working directory, you can set the print C argument to true to do that. Some other arguments should be familiar to you. It has a plot argument. By default, it's true, but if you just want the confidence interval in a table and don't want to see the plot, you can set plot to false to suppress the plot. It has a main argument. That should be familiar because it's pretty ubiquitous in plotting functions, not just in this package, but just across the R universe, to generate a custom main title for the plot. It sort of has a generic one generated by the function, but we could probably write something better, specifying it with a main argument. And it has a xlab argument to create an x-axis label, and xlim argument to modify the limits of the x-axis if you want to expand this or contract the x-axis. As I mentioned, with the basic required arguments, the x limit is like automatically generated by the function to focus in on the area of difference, but that potentially is misleading or can be misleading. So sometimes you might want to use the x limit argument. Like for example, in this case, I might say, well, I want to show the average number of years on a more sensible scale, so I will do it on a 0 to 30 scale. So plotting it on a scale that runs from 0 to 30 years. And now if we see it, because reference line at 0, we can see where the point estimate falls, and the scale is now big enough, running from 0 to 30 years, that you can no longer see the confidence interval. But it would give you kind of maybe a better indication of how well we know the average number of years that Americans lived at their current address based on this data, and how confident we actually are about that estimate. Now, by default, we plotted the 95% confidence interval and generated the table for the boundaries of a 95% confidence interval. But if we wanted to change that level, we could use the level argument and set that equal to the desired confidence level as a percentage. So for example, we could change it to the 99% confidence level to get a 99% confidence interval boundaries, or change it to a 90% confidence level to get the 90% confidence interval boundaries. And there'll be slightly different numbers depending on how confident we want to be. Another option, and I think this would be seldom used, but it is possible to use this, is a option we have called pop.sd. And this would be used if you know the population standard deviation for the variable. In most cases, like with this NES address years variable, we can estimate the standard deviation and the variance of address years based on the sample data, the same way that we use a sample mean to estimate the mean in the population. We can estimate a sample standard deviation to estimate the standard deviation in the population. There are perhaps some rare cases where you might know the population standard deviation and population variance of the variable you're analyzing. As we suggest in the book, it comes up in some rare instances like standardized testing, or perhaps some mechanical process you wouldn't really see in political science situations very often. But just to show you what would happen, let's say we knew the population standard deviation was what would be a plausible value for number years moved. So let's say 5. That the standard deviation of the number of years that people move from their address is 5. And it seems maybe relatively plausible. So now if we input that value and we set pop.sd equal to 5, the function will say we're no longer estimating the population standard deviation from the sample. Instead, we know it. It's 5. And it will calculate the interval based on that supplied population standard deviation. And it looks fairly plausible. It must be close to what the sample estimate is. So report those lower bounds. And then it's hard to see this just from the results, but what it's actually doing is it's switching the probability distribution used from a t-distribution, which is typical for sample means, and it's switching it to a normal distribution, which can be used when the population standard deviation is known. As I said, this particular argument, pop.sd, it's probably rare to use that. It would be seldom known in political science applications, but it's possible that you could use that, and I'd say like especially possible that you could use that on if you had a homework problem that told you to use a certain population standard deviation for a problem. But generally I would say it's going to be rarely used with the CImean function, because the CImean function is meant to operate on variables in data sets. So usually analyzing sample data and using the sample data to estimate the population standard deviation. It's rarely known, especially when you're working with sample data. And then, as I mentioned in an earlier video about the SAMP distribution C function, SAMP dis C function, that is used where you're given the sample statistics and the standard error of the sample statistics. So if you're given the values, like say you had a problem that told you, the sample estimate for a statistic is 11.98 and the standard error is 5, or it would be a lower value than 5. The standard error is 0.5. What is the confidence interval? If you're given the point estimate and given the standard error of the estimate, and you're not estimating it from a data set, that's a good time to use the SAMP dis C function. So if you're given the statistics to work with and asked to create a confidence interval from the statistics you're given, use the SAMP dis C function. If you're pointed to a variable in a data set and asked to generate the confidence interval for the values of that variable, that's when we're using this CImean function, and hopefully You now know how to use the CImean function, its basic arguments, as well as some of the options it has to customize the table and the plot.